Okay, this is the first video where we want to discuss a little bit more about three-phase circuits. Some of this will be a review of class the other day. This is a slide that illustrates the three parts of a three-phase circuit. You consider the source as one of the components, then you have your lines as a second component, and you have your load as a third component. And this is independent of how the three-phase is actually configured. You always will have a source, a line, and a load. So the terminology is important because people will talk about things like load voltages and line voltages and line currents, and you need to understand what that's referring to. So basically, the configuration that we discussed last time in class and that we'll discuss first in this short video lecture is the Y configuration. In the Y configuration, you have three separate voltage phases. They form a Y and they come together at a common point in the middle. The top circuit here is referred to as a positive phase sequence because going from phase A to phase B to phase C means you're having a clockwise motion. Typically, A is referred to as the reference phase, and so it's given a phase angle of 0. B would be out of phase with A by 120 degrees, and because this is a positive phase sequence, that's a negative 120 degree phase angle. And then C is another negative 120 degree phase angle, which puts you effectively at a positive 120. So you can see you go from a 0 degree phase to negative 120 to positive 120. That's a clockwise motion, making you end back up at A. So clockwise is correlated or associated with a positive phase sequence, as opposed to the bottom figure where from A to B to C we're going in a counterclockwise direction. That's referred to as a negative phase sequence, and you can see the associated phases on each leg of the three-phase voltage associated with that negative phase sequence. And you can note that as you trace from A to B to C, you're going in a counterclockwise motion, hence a negative phase sequence. Independent of the phase sequencing, if the source is balanced. Now, what does a balanced source mean? A balanced source means each leg of the three-phase voltage source has the same magnitude, and they're out of phase. Each is out of phase with each other by 120 degrees. So if this is a balanced set and you take the phasor sum of A, B, and C, independent of whether it's a positive or a negative phase sequence, the phasor sum ends up being 0. This is just an example of what a three-phase voltage source might look like. In this case, we're illustrating a generator that has a rotor with a single set of windings and then three separate pairs of windings, an A phase, a B phase, and a C phase. The rotation ends up coupling these coils in different ways with each winding phase, and the way they're physically positioned results in them being 120 degrees out of phase with one another. There are two ways to connect a three-phase ideal voltage source. Now, what makes it ideal? What makes it ideal is that there aren't any losses associated at the source end, so you don't see your typical resistive and inductive losses that we know are present in any source. So for the ideal three-phase source, there is the Y connection, which we've looked at before. There's also the delta connection, which is shown here, that we have not illustrated before. Both connections have an A, a B, and a C coming out in the Y connection. You'll also typically have a neutral wire. Notice in the delta connection you don't have a neutral wire, so there is no, in a delta connection there's nothing that would look like a voltage between the A line and the neutral wire. It just doesn't exist in that configuration. Now here is the real world model. As we discussed in class, almost all sources have an inductive reactance. So typically that's modeled as the inductive reactance of the windings, the resistance of the windings, and so your actual output then does incorporate that impedance into the model. And so your real A, B, and C terminals actually come after that source impedance is modeled. Same is true with the delta connection. It's just the impedances still will appear in series with the source for all practical purposes, and you end up with the same kind of model. So when you actually connect, and we'll start with the YY system, because the general approach is, if you have a delta connection, the general approach is to convert that to a Y connection, particularly with regard to the load. So we'll learn the Y to Y connection system fairly well, and then we'll convert that to a Y to delta, or show how to convert a Y to delta back to a Y to Y. So as we discussed in class, you have, along with your generator or your source, you have your impedance, so that this blue box actually encompasses what would be your actual source. A, B, C, and the neutral are the terminals that you're actually able to connect to. Then each leg, the A, the B, and the C, all have an associated impedance that is related to the inductance and resistance of the transmission line that takes you from the source to the load. There's also an impedance in the neutral wire that would theoretically be the same, because typically you'll use the same materials, same travel distance, same configuration. And then finally at the load end, the load also hooked up as a Y. You can see we switch on the generator end from smaller letters on the load end to larger capital letters. So that's just a notation thing here. And you notice they're also hooked up with a common, and the neutral wire then is tied in to the common point on the load end as well. So some terminology. The voltages between big A and big N would be referred to as the phase voltage at the load. It's phase voltage because it's the voltage across a single phase of the system. So A to N would be a phase voltage, B to N would be a phase voltage, C to N would be a phase voltage. The currents here, I little a big A, is the line current. But it's also the current in a single phase because it's the current through the load. So in a YY configuration, what is referred to as the line current, which is the current through the transmission line, and the phase current, which is the current in a single phase at the load end, are the same. Whereas the voltage, the phase voltage, is the voltage between the point on the line and the neutral wire. So it would be a little bit, the phase voltage and what we would refer to as line-to-line voltages would be different. So in this class, we're only going to work with balanced three-phase systems. So what exactly makes a three-phase system balanced? The first thing is that the ideal voltages coming out of the voltage source or generator are the same. They have the same magnitude. They are offset by 120 degrees. It's also important that the impedance of each phase of the voltage source is the same. So this would mean that your generator impedances for A, B, and C are all the same. It also means that the impedance of each conductor is the same. So your transmission line from generator to load needs to have the same impedance. And finally, it means that the impedance of each phase of the load is the same. So if you were to go back to the previous slide, you can see you have impedance A, B, and C. So for this to be completely balanced, each impedance must be different. So one comment that I want to make here that's relevant to your homework is if the sum of all three impedances, ZA at the generator, the line, and the load, if you add all of those together, and that's equivalent for the A phase, the B phase, and the C phase, that does not necessarily mean the system is balanced. The only way the whole system can be balanced is if at each individual component the impedances are the same. So I believe that's one of the examples in one of the homework where the total impedance is the same. That does not make it a balanced system because you would have to be the same at the generator end, in the line end, and at the load end. So in a balanced system, the significant thing about that is that the voltage on the neutral line between the generator and the load is 0, which means you have no current in the neutral wire.